Well, it's sort of a combination of, it's a continuation. I was going to start off talking about the aurora, which is an aspect of looking at the solar activity. And then I've got some quite exciting images from members of the club to share. I was hoping actually to use some images from members of the club for their aurora, but I wasn't able to do that, unfortunately. So those are stock images, but the best I could do was to put a picture I took of the Southern Cross in, just to remind you that that's the Australis and that's the Borealis, which is in the north. So the issue is what causes the aurora and why can you only see it at high latitudes? One thing you should know is that it's largely green, but if you look at this one, the Australis version, you see it's green underneath and it's red on top, which is actually quite significant for reasons that I will explain as we move on. So the question is as to what causes it. Well, the answer is it's the solar wind. Michael was mostly talking about electromagnetic radiation, which takes 8 minutes to reach Earth. It travels 3 times 10 to the 5th kilometers per second. The solar wind, on the other hand, is mostly electrons, protons, alpha particles ejected from the corona. And they take, well, the escape velocity on the surface of the sun, 600 kilometers a second. So the actual velocity by the time they reach the Earth is about 250, 800 kilometers per second. So generally a corona or a solar wind takes about 1 to 2 days to reach the Earth. And it's the interaction, as I'll explain in a minute, between the solar wind and the Earth's atmosphere that creates the aurora. So if we move on to the next slide, these are a couple of images taken by Ed Hanlon of the solar eclipse in August 2017. With the sun covered up, you can really see the aurora ejecting particles in all directions at all times. So what happens is that the radiation is extremely narrow band. As Michael explained, line spectra. The green transitions is a transition in the oxygen atom between certain energy levels, and which are actually forbidden. And quantum mechanics determines which transitions between different quantized energy levels are allowed and which are forbidden. This is a forbidden transition, but like my grandchildren, who are very well behaved most of the time, sometimes they break the rules, and you get transitions occurring with a long decay time. And the long decay time, in accordance with the uncertainty principle, implies very narrow line width, and so the line width of the green coloring is about 0.035 angstroms, which is absolutely tiny, and that gives us an indication as to where we might find it, because in order for the excited oxygen atoms, which are excited by the mainly electrons coming in on the solar wind, to radiate, they have to live long enough without bumping into other atoms, which means they need a long mean free path, which implies a low pressure. And the region where you get sufficiently low pressure is around 100 to 150 kilometers above the Earth. So that's where you see the green. And the red transitions are even more forbidden. The decay time is around 110 seconds. So that means you need an even lower pressure. And so the red is going to occur above the green between about 150 to 200 kilometers above the Earth. So that the major part of the aurora is created by electrons interacting with oxygen atoms in the upper atmosphere between 100 and 200 kilometers above the surface of the Earth. There is some other excitation going on, some protons, but by and large, the excitation is due to electrons interacting with oxygen atoms in that range. And so the next question is, why do we only see the aurora at northern or southern latitudes? And the answer is the Earth's magnetic field. The force on a charge, which is moving in a magnetic field, is the vector product of the velocity vector, which is this direction, and the magnetic field vector, which is these field lines. And that's given by the left-hand rule. If you point one in the direction of movement, one in the direction of the field, the other one will give you the direction of the force. You can see they're all at right angles. So what happens is when an electron comes along here in the solar wind and hits the magnetic field lines that are at this point essentially parallel to the Earth's surface, it gets directed out of the plane of the paper. But if you look at the northern latitudes up here or the southern latitudes, you're going to, there is a component or a major component of velocity which is actually parallel to the field line. So what happens is they hit these field lines, spiral down into the Earth's atmosphere, and when they get to between 100 and 200 kilometers above the Earth's surface, they excite the oxygen atoms, which then decay with, as I say, relatively long decay times, 1 second for the green and 110 seconds for the red. So that's really the reasoning why you only see the aurora at high latitudes. And there's a diagram here showing the interaction of the solar wind with the Earth's magnetic field, which, is actually, in practice, of course, a lot more complicated than that rather simplistic explanation I gave, but the basic principle is the same. And as Michael pointed out, the solar wind would be very harmful to life on Earth. And in fact, if we didn't have the magnetosphere, we wouldn't be here. But the interesting thing is that there's a kind of sort of double edge to it, in that the Voyager spacecraft has just, which is now in interstellar space, has discovered that the solar wind, when actually it gets to the edge of the heliosphere, does actually protect the whole solar system against highly energetic cosmic particles that would otherwise cause us problems. So it's sort of also beneficial. The monitoring the aurora does give us, as Michael indicated, an indication of solar activity. And when you get these coronal mass ejections, what happens is a rapid increase in flux, and I can make it actually, oh no, I'll make it laser, yeah. It distorts the magnetic field, so you get, the field lines get pulled round and then the particles spiral down at lower latitudes than would be the case in a normal equilibrium. And then this is just a simple diagram I made to show that if you imagine something 200 kilometers above the Earth's surface, and you just do the maths, you see that you're not going to, you will only, if assuming you're standing on the surface of the Earth and not on a mountain or something, you will only see something at 200 kilometers from about a 14-degree difference in latitude. So you've got to be less than that from where the aurora is occurring in order to see it. Like everything else, it is a lot more complicated, again, than my simple explanation. And there's a very good chart here by Serge Strubankt, who's the reference is there, which is clickable, that shows you in great detail what happens with when various events occur, which the types of flares you get. If you get CMX class flares, X class, the strongest flares, you get coronal mass ejections, which do various things on Earth, causing blackouts. You've got effect on the aurora, effect on RF, and the whole solar activity is very influential on a whole lot of things that happen on Earth. In particular, here we've got the aurora down here. You get very intense aurora at lower latitudes because it from these high energy particles and coronal mass ejections, which distort, they create a geomagnetic storm, distort the Earth's magnetic field. And the other aspect, which is of interest, of practical interest, which again Michael alluded to, but it's HF propagation. The ionosphere is actually made up of a number of different layers that are created by different kinds of radiation from the sun. There is the F1 and F2 layer, which are very important for high frequency propagation. So if you want to communicate with someone on the other side of the Earth before they had satellites, or if satellites fail for some reason, you need to bounce off the ionosphere. And there's also the the propagation characteristics depend heavily on the sunspot activity in quiescent period. Well, first of all, the D layer here, which occurs only in daytime, is a blocking layer. HF above about 4 megahertz does not get through it. So you don't get much long distance propagation in the daytime. And that's why you probably, but at night times, it's this layer completely disappears. And that's why if you have a shortwave radio, you'll find that you get a much longer range during the night than you do at the daytime, in the daytime. And the other aspect, yes, with solar minima, you don't get much propagation above about 15 megahertz. During sunspot activity, you go up to 30 megahertz and beyond. So it makes a huge practical difference to radio communication. A very good reason for And that's why people study it in so much detail. Now we have, these are some images from members of the club. This is Ed Hanlon, who took a series of images of the eclipse in 2017. You can see the series going right through from partial to, you've got the solar beads there, total eclipse, and then going through back to the end of the eclipse. And these were taken in Oregon with his reflector and solar filter. I have some more images here. James McWilliam took a series of images of the eclipse. And this, yet another one, Frank, I'm afraid I don't know Frank's second name, but here we have some more images taken by members of the club. This is a number of methods of taking images of the sun have been mentioned, but this is one I found which is purely accidental. I took in Desolation Sound on the 5th of September 2017, which just happened to coincide with the major flare on the solar X-class flare on the sun. But I took that through the wildfire smoke, no filter at all, except the wildfire smoke. So that was a sort of novel way of taking an image of the sun, but not one that I would recommend. These are some images I just took recently. Well, that one, that wasn't recently, that was my image of the eclipse taken from here in Seychelles. But these I've taken recently with my Mylar filter. And this one is a blow up of that, which I took through a 2x Barlow. And I haven't quite figured out what the reason for the coloring is, but it always seems to crop up in my images. So I don't know if that's an artifact of the system or whether it's just is genuine. But anyway, and you'll note here that I measured the distances. And if we go to the next slide, I did a little bit of maths, and I found that quite conveniently that if you do the math, all the zeros cancel out. If you take your pixel pitch and divide it by the focal length in meters, and you take d as the Earth-Sun distance in millions of units. So if it's kilometers, 148 million kilometers. If it's miles, it's 90 million miles. You get the distance in those units on the sun. And you can very easily measure that in Photoshop. You just go image analysis, and use the ruler tool, and it tells you how many pixels there are, and you just use that formula and you get the distance. Very simple. This is an image that Michael took, which is quite interesting because he's plotted a sort of inverse plot of temperature. It's a sort of 3D thermal map of temperature. So if you look around the sunspots, so you can see the higher temperature, 5,000 Kelvin, leading to the lower temperatures in the darker regions. There's a strong magnetic field. It gives you a kind of another novel representation of the sunspots. This is one taken with a Herschel wedge by Michael. It's pretty clear, as is that one. And then Michael was talking a little bit about H alpha. I have currently got the club's H alpha filter, and I was talk a little bit about that. But it's basically it's a dichroic film, which is a thin film interference filter. And it goes through into a Fabry-Perot etalon, which is kind of a pair of, it's a bit like a laser without a lasing medium. It's a sort of pair of spaced plates that generate an interference pattern that allow you to select out with great precision your particular wavelength, which is hydrogen alpha, which is 6562.8 angstroms, or an angstrom 10 to the minus 8 centimeters. So that's about 656 nanometers. But the bandwidth is quite narrow. It's half an angstrom, and it's tunable because you can change. What you do is you change the temperature of the air in the etalon. And as you change the temperature, you change the optical path length, which is the refractive index times the actual path length. And you can tune it in steps of 0.1 angstrom. And that enables you to get a very precise match with the hydrogen line that you're looking at, which is this one. It goes from N3 to N2 in the Balmer series. But it also it allows you. It's going to change because with the motion of the hydrogen atoms, there's going to be Doppler effects, which will slightly change the frequency. So you can tune it to get a very precise view of the sun in hydrogen alpha. And this is one that Michael took in hydrogen alpha, and again you can see the detail. See how it compares with just a white light. And again, yet another one, Michael hydrogen alpha, and another one. These are all Michael's pretty detailed images of the sun, all just basically because you're just looking at that transition in the hydrogen atom. And ignoring all the other stuff. But the sun is mostly hydrogen. These are some from other members of the club. We've got here prominences, sunspots, filaments, and plages. Again, hydrogen alpha shows you what hydrogen alpha filter can do. These are Dan Sligzewski's. This is a pressure tuned scope. So that presumably is hydrogen alpha DSLR. So that presumably is changing the wavelengths by changing the pressure within the etalon, which will vary the spacing between the reflector, the mirrors at the end. And finally, this is just an example of the club outreach, showing the sort of events that can happen. As Michael said, it's very convenient being able to do some astronomy during the daytime because it's warm, not freezing cold, and it's something that sort of is convenient for people to join in and enjoy, and it has a very practical application, and that's it. Any questions?
Thanks, Richard. That picture you showed of the sun there, really close up, that was taken with the quark just after we got it.
That one,
this one,
yeah.
What's the quark again?
It's a hydrogen alpha eyepiece, is how they describe it. It's the latest from the people who brought the Daystar filters onto the market.
Now that is a stacked image, though, is it not? Or
no, that's a shot. Oh,
Well-
sorry. No, that's 300. Yeah, it says it there.
Yeah.
Back at 300.
Oh, there it is. Okay.
Yeah.
My thing is blocking.
That's the one I have, isn't it? That's the one I described. It's
Correct.
Yeah.
Work. I should get one of those.
Well, I
What's
think
it worth?
1200.
Oh, maybe not.
We found that the popularity with members of the public, looking at the sun, being able to show them sunspots and flares and so forth, it was always a big draw. And so we applied to the gaming grant authority here in BC and said that we could enhance our outreach experience if they would provide us with equipment to look at the sun. And at the moment, it was members' own personal equipment that was being used.
Right.
And of course, there's a risk with that. And also, members, we're an elderly group, we're not going to be around forever. Anyway, they accepted the argument and they gave us some money. And with that, we bought a few pieces of equipment. This was one of them. So thank you, gamers,
Well,
gamblers.
Those, by the way, I stacked. No, that one is stacked. I think that's about 10 stacks.
I'm still interested in those quark exposures because they're actually somewhat like some of the shots. I don't know that you get some similar granulation with your I forget what you call it, like the prism or whatever.
Wedge, Herschel wedge.
Herschel wedge.
Herschel wedge. Now, so is that a video clip? So 300 stacked images, but is it like a video clip and does it darken things quite a bit? Like what sort of exposures? Like, I'm curious about that sort of thing.
I'd have to go back and look at that particular one. It's quite a dark image in the case of the quark. It's a lot less dark with these from the Herschel wedge. Those are you tend to adjust the exposure depending upon whether you're trying to capture flares or whether you're trying to capture surface details. And in fact, you probably do both. You would probably create a few images, a few hundred images at short exposure and a few at longer exposure. But we're only talking about tens of fractions of a second. We're talking about very short exposures.
Oh, wow. Okay. Because I was wondering if it was like the origin of the original images, if they were like a video clip at 60 frames per second or like an intervalometer that's taking a shot, maybe, I don't know, every
No, it's frames per second.
second or something like that.
This is the one I use. This is a Skyris. This does 90 frames a second.
Wow.
And it just goes in the eyepiece.
And I think my Chameleon, which is point gray, I think it's 60 unless I change it down.
And would your Malin cam sort of get somewhere in that ballpark, like in terms of resolution and detail and stuff, or no?
No, it wouldn't.
Well, very impressive. Nice.
I have a personal experience with Auroras. It was when I was still doing anesthesia, and I used anesthesia as a ticket to ride, and went, and I wanted to spend a period of time around the shortest day and also the longest day in Inuvik, which is above the Arctic Circle. And during the nighttime, the December stint, I heard my colleagues telling stories of the excellent aurora that they saw the previous night, and I was all keen and motivated. And so I went out and looked up, and midnight in Inuvik on mid-December. And besides experiencing the cold, I didn't experience any aurora at all. So next morning in the operating room, everyone was regaling the wonderful aurora. And so I went out again and looked and saw nothing. And then instead of looking north, which is what I was doing, that's where you look to see northern lights. I looked straight up, happened to look up, accidentally looked straight up, and there was this green snake going across the sky. And it didn't look like a sheet of northern lights. It just looked like quite narrow green snake snaking across the sky. And so I had to learn what I learned subsequently, or I figured out what I was looking at, is that I wasn't seeing a side view of the curtain of northern lights, is that I was actually underneath the curtain, and I was looking up at its edge from the bottom of the pleated sheet of northern lights, I thought. Anyway, that was my interpretation. And the other thing I learned, was forced to learn, was that I understand, Richard can back me up or refute, is that the location of maximal northern lights isn't the North Pole. It is, in fact, around the Arctic Circle. That's the latitude where the northern lights are maximum. So I was above, but not by much, the Arctic Circle. So that's why I couldn't see them looking north. That's not where they were. They were in round figures straight above. So anyway, that's my personal.
That's right. Because
Okay.
as you get to north of these field lines, then
Okay, folks.
happens.
Folks, I need to cut in here. I know we got a lot of discussion and it was really good, but we're almost at 9 o'clock and we still have one more presentation. Is there a way maybe we can bring some of this up again at the next meeting and bring some of these things in? Because I don't think we have time for a break. I think we need to go right to Bruce Fryer's Skies of Night. Did you have
Were there any more questions though for Richard?
Yeah, that's what I'm going to say. Is there any more questions before we go right off to Bruce? But we have to make it short.
Well, I was going to ask Richard why it was that when I was in Lapland, 600 kilometers inside the Arctic Circle, that I didn't see the Northern Lights. And Brian has just described the solution.
Yeah,
that
well,
I was too far north.
I was just
Or you were looking in the wrong direction.
I guess so.
Yeah, I was just about to answer that question, because if you think about it, if the field line is too vertical, then you're still the left-hand rule. The solar wind's going to get deflected away from the Earth, so you're not going to see them.
Pictorially speaking, maybe just because you were talking about directly overhead, and that is pretty interesting, Brian, because you were up like way north, so you're indeed right under like where the aurora hangs out, and And when I was shooting Aurora, it was like in Fort St. John, quite a bit further south, but still kind of north. So to get direct overhead Aurora, you would have to catch it on, a strong solar storm. So there's like these sort of two images, which, I mean, they don't come out very well, but that's like directly overhead. You can see the tips of trees and the kind of overhead snake you were talking about. Here it looks sort of like a bird, but yeah, they were like directly overhead and almost like boiling green light.
Right. Well, the ones I saw were, the line was much more defined in your images. And it was brighter, just because when you're right down, I'm thinking, when you're right down below, it's the equivalent of stacking all of those images. I was looking at the full depth of the sheet right from the bottom. And so it was very bright and very thin and kind of very dense green snake.
Okay.
Anyway,
Okay, gentlemen, we do need to get this kind of short, get moving on, because we're going to be way past our time. Any last final questions for Richard or Michael? Otherwise, can we cut over to Bruce?